Hey, we've got Darren already.
Good morning.
Good morning. What's it like in your neighborhood?
Wet, cloudy, and pretty cold.
Yeah, same here. Where are you located?
I'm down by like 121st. I'm near like the Glenpool northern
Yeah,
border.
okay, down south. I'm at 31st and Mingo, kind of in the middle.
Hmm.
It's kind of a convenient location. I can pretty much go any place from here. Doesn't take too long. You got to head
Yeah,
north to go any place, don't you, Darren?
pretty much. Yeah, I got to go all the way to the Northeast campus for most of my classes. It's really unfortunate, but I mean, what are
Yeah,
you
it
gonna do
is.
about it?
You should have majored in sociology. You could have gone to the Southeast campus. Wonder who else we got here. Let's look and see. Oh, we've got Ashley too. Good morning, Ashley.
Good morning.
Yeah. Hey, you guys got me all to yourselves here for about 3 minutes. Do you have any questions?
I don't think so. I mean, my only question would be like, when do you think you'll have the tests graded?
Oh, they're graded and posted already. I mean, we're
Oh,
talking
what?
totally, totally efficient operation here.
Wow.
Let me look and make sure I'm not lying to you here.
No, yeah, I see it.
No, they're there.
Wow. How'd you?
Yeah.
That's impressive. My all my other classes, it takes like a week for them to grade the midterm or exams or whatever.
Yeah, we'll get used to it. That's the way it's going to be when you go to OSU. And plus, you won't have your instructor do it. It'll be an assistant. You know what I mean? A teaching assistant. So you got the real thing with me.
Thank you.
Yeah, I'm the real thing. Kind of like Coke. Coke is the real thing. Well, okay, you guys don't have any questions. We have 2 minutes left though. We're going to study shear loading diagrams, bending moment loading diagrams. I'm hoping that you've studied those before. Let me ask you, the two of you, let's see if there's any more. Yeah, now we've got Ben Seaman, Ben Harris. Let me just ask the group there, have you studied these shear and bending moment loading diagrams before? Have you?
It sounds familiar, but I need a refresher on it.
Okay, well, we're definitely going to refresh you because I've taught this class and I've had students that have come to me and they've had that before, which is nice. So it's not totally strange. There's four kinds of loading diagrams. Let's just briefly go over those. There's four kinds of loading diagrams. The normal force loading diagram. Well, let me ask you this. How about one of you? Alex is with us. And Ashley.
Hello.
Yeah, hello. Hey, Alex. Give me another kind of loading diagram. There's four of them. What's another one?
Bending.
Yeah, there's the bending. The full name of it is the bending moment loading diagram. Well, I already wrote loading diagrams. I don't need to write it again. And there's two more. How about another person? Mohammed's with us, and Ben Seaman, Ben Harris. Anybody speak up? What are the other two? Go ahead, anybody.
Shear
Nicholas.
force is one, right?
Yeah, shear force. There you go. Shear force.
Torque diagrams.
What was it?
Torque diagrams.
Yeah. The torque. Good going, Mohammed there. And see, each one of these has some important equation that goes with it. This one here, we know and love. It's just normal force over area gives you your normal stress. And on the torque, the shear stress is equal. That equation has a name. Now you might have forgotten it, but it's called the torsion formula. I think we've just been working with that. The bending moment loading diagram. We haven't studied that yet, but we will. That equation is called the flexure formula, and that's in our chapter we're studying. And on this one here, now we've studied this here. You should know what each of these are. And we've studied this one here. But now these two, we haven't studied yet. But we're going to study this one here soon, very, very soon. And then the next chapter after that, we'll study this one here. But see, in order to use these, you need this normal force loading diagram. In order to use this one, you need this bending moment loading diagram. In order to use this one here, you need the torque loading diagram. In order to use this equation here for shear stress, you have to have the shear force loading diagram. The reason why the loading diagrams are so important is they give you the values that go into your equations for your stress. Remember, stress is the most important thing in this class. This here is called normal stress, and that's called shear stress. And so you can get normal stress with a normal force, but when you bend something, you can get normal force also. Here, I'll demonstrate. I've got my ruler here, and here's my ruler. And if I bend this ruler this way, I've got tensile stress on the top and compressive stress on the bottom. If I bend it this way, I have tensile stress on the bottom. See the little molecules of wood on the bottom are being stretched. That's tensile stress. But the wood here on the top of my ruler is being compressed. That's compressive stress. See, when you have a bending moment, you can get normal stress, tensile and compressive normal stress. That's why it's so important for us to know how to do the bending moment loading diagram. I have students that neglect these. They just go right to these equations here and they work on these equations, but they get it wrong because you've got to get the right normal force. You've got to get the right bending moment. You've got to get the right shear force. You've got to get the right torque. If you get those wrong, you'll get the wrong stresses. Is there any question about that? Okay, well then, if there's no question, class has started, and let's get to work here. Let me make some room here. Now there's three ways or three approaches to doing. Our topic right now is shear and bending moment loading diagrams. And there's three approaches. One is I call, see what I'm trying to tell you right now is how do you make a shear force loading diagram and a bending moment loading diagram? How do you do it? Well, there's three approaches. One, first, I call inspection. And I'll try to explain what I mean by that. And then the second method is sections. The problem with the sections, taking sections on a left-hand section, you always take left-hand sections, is it's very tedious and time-consuming, but you can do it that way. And then the third way is with the equations. Now the equations we're talking about are these. Those are the four equations that I'm talking about. Now, these are all explained in your book, of course, and they're derived in your book. Let me see if I can find the page here where they show you where they came from here. Just one tiny minute here. I'll show you where they got those. They're on page 270. These equations are in your book on page 270, and you can read how they derived them. I think I'm going to spare you the agony of the derivations, but I'm going to show you how to use those equations. It's one way of getting at the diagrams. There's three ways, and we're going to show you those. Well, let's do some problems then. There's your theory. Before we do the problems, do you have any questions? Just go ahead and ask if you do. I'm going to put down the homework. It looks like your homework number 19 is problem 612 on page 283, and it's due, what is today? Today is Tuesday, right? So that'd be due Friday. That's due Friday. Today's the 20th, so that'd be the 23rd, wouldn't it? All right, let me look on my calendar here. Today's October 20th. Yeah, that's right. So you got a little homework there to keep you happy. And I think we're ready to work a problem. Here's your chance. Did you have any comments or questions? Okay, well, let's do a problem. I was thinking about doing F6-8. F6-8. Let me find it here. F6-8. There it is. It's on page 281. Page 281. F6-8. And the way you do these shear and bending moment loading diagrams is first you draw the free body diagram. Okay, let's do that. Now I'm going to erase all this unless you have a question, because I need the room. All right. Now your first job is to write the free body diagram. Okay. Well, this looks like a beam with a distributed load. All right. Come on now. We've got a beam with a distributed load. Okay, now this, I think they use a little symbol W to represent the distributed load, and it's 20 kilonewtons per meter. I'm going to run into my other, let me scoot it over here. W is 20 kilonewtons per meter. And then they have another force here of 20 kilonewtons. I like my forces in red, so let me put that in red. 20 kilonewtons. And let's label all this stuff. This is A right here. Yeah, there we go. There's A. And this is B. And that's C. Okay, this is 4 meters and 2 meters. Okay, I think that's about it. Now this distributed load has a resultant. the distributed load, let me refresh your memory about that. The resultant of a distributed load is equal to the area of the distributed load. You see this distributed load? It's a rectangle. They taught me in school many years ago that the area of a rectangle is the base. So the resultant is the base, which is 4 meters. That's how long the bottom is, times the height, which is 20 kilonewtons per meter. And if you do that, I'm getting 80 kilonewtons. How about you? Now we know what the resultant, see, that's the resultant. It's 80 kilonewtons. There we go. Now we know the resultant. There. All right. Now the next step is we've got to get all the external forces. So we drew the free body diagram. I need to tell you something else too. The resultant of a distributed load is equal to the area, but the resultant of a distributed load goes through the resultant of a distributed load goes through the and I'm gonna call on one of my excellent students here. Julian, unmute and say hello, please, Julian.
Hello.
Yeah, hey, Julian. You know the resultant of a distributed load is equal to the area of the distributed load, but it goes through what, Julian? Do you know? What does it go through?
The center?
Yeah, that'll work. That's good. I buy it. Julian knows what he's doing. And the fancy name for it is centroid.
Oh, yeah. Sorry.
You're forgiven. The center is okay with me. Well, see, the center's right here. See? I mean, there it is. It's just a rectangle. There's the center, and it goes through the center. Okay. So we got that. Now, the next step is we got to get all the external. We need all the external forces on this free body diagram. Well, there's one here. Why don't we call that A, maybe? And then there's one here. Why don't we call that B? All right, now we got all the external forces in red. See there? Isn't that nice? But we've got to find A and B. Now, the way you do that is you take your sum of the moments. You can take them about A or B, it doesn't matter. But if you take them about A, you get minus 80 kilonewtons times 2 meters plus B times 4 meters minus 20 kilonewton times 6 meters equals 0. That's the sum of the moments about A. Now I'm going to call on one of my excellent students here. I picked on Julian a minute ago. Let me pick on Braxton. Braxton, unmute and say hello, please, Braxton.
Hello.
Hey, Braxton, how come this moment here, this 80 kilonewtons times 2 meters, how come it's negative, Braxton?
Because it's going clockwise around A.
He's got it. He's got it. That's right. It's going clockwise. it's going like that. Can you guys see that? See that 80 kilonewtons? About A is trying to make it go clockwise. Braxton understands. All right, I'm going to shut up for 45 seconds or so. And then I'll call on one of my wonderful students. We need to know what B is. There's one unknown in this equation, and we can get it. Go for it. Okay, let me find a wonderful student here. Let's see. We'll go to my friend Alex. Alex, unmute and say hello, please.
Hello.
Hey, Alex, have you figured out what B is out of this equation yet?
Well, I scrambled for my calculator, but I got 70 kilonewtons.
Very good. Good
Perfect.
going. We think B is 70 kilonewtons. Now see, the sum of the forces has got to equal 0. Now on the forces, we have A going up. Is there room to write this? Yeah, maybe. We got A going up, minus 80 going down, plus 70 going up, minus 20 going down equals 0. I can almost do that in my head. I think A is 30. See, if A is 30, I think the sum of the forces in the y direction is what we're doing. The sum of the forces in going up is 30. See, 30 and B is 70, makes 100. And 80 and 20 makes 100 going down. So, hey, we've just done that. Here's how you do these problems. Here's how you make these shear bending moment loading diagram. You draw the free body diagram, put all the external forces in there, and then you solve for the unknowns. And we just did that. We're doing great. We got all the unknowns. And now I can erase all this stuff. I don't need it anymore. Let me erase all this. But see, we haven't even started on the diagrams yet. Okay, now I told you there's three methods for doing the diagrams. Here, let me draw you your shear loading diagram. This is going to be the shear loading diagram. And down here, we'll have the, come on now. We'll have the bending moment loading diagram. And I told you there was three ways to approach it. One was what I called inspection. You see that smooth pin right there? At A, smooth pins can't give you any twist. It's like a doorknob that somebody's put grease on. Go get a can of Crisco lard and smear it all over your doorknob, and then try to open it. Well, see, it's kind of hard to get a twist going on a smooth pin. So there's going to be a zero bending moment right there where that smooth pin is. I call that inspection. You just kind of look at it, think about it. There's going to be another one here. It's not as simple as a smooth pin, but see, there's no twisting going on. There is a force, but there's no twisting going on right there. See, so that'll be zero. But you can have bending moment every place else. So I got those 2 points by inspection. Now about the shear diagram, I'm going to use what they call sections. We're going to take a section. Remember, there's 3 ways to do this: inspection, taking sections, and using the equations. We'll do all 3. Now we can take a section. Take a section right in here. Take an imaginary hacksaw and just take an imaginary cut through your beam there. It's true that you have a tiny bit of distributed load acting on that section, but pretty much you're going to have a force going down, which is a shear force equal to that 30 kilonewtons. Now there's a convention that we'll just tell you about. If your shear force is going down, that's considered positive. Let me show you that in the book. Go to page 264. And do you see a picture here where they got the shear going down on that left-hand member? That's considered positive. Now, if you have a right-hand member, the shear going up is considered positive, but we always deal with left-hand members. So the shear is a positive 30 kilonewtons. So we'll just mark it right there. You go, 30. We've got 30 kilonewtons right there. And then what happens is, well, you can use the equations. See, the equation goes like this. Now the distributed load is 20, but it's going down, so it's a minus 20. And so the slope of the shear loading diagram is minus 20. So if you go over 4 meters and the slope is minus 20, you drop 80. So that'll put you down here to minus 50. There we go. A little bit sloppy, but minus 50 kilonewtons. Now, if that didn't make sense, you can look at your change in your shear. Well, see, going from 30 to minus 50, that's a change of minus 80. And going from here to the 4 meters, see, that's 4 meters. If you take minus 80 kilonewtons and divide it by 4 meters, you'll get minus 20 kilonewtons per meter. Minus 20 kilonewtons per meter. So you can get it from that. Well, we did good on that. We're using the equations now. We've used inspection, we've used sections, and now we're using equations. I bet you guys like the equation. Here, let's see what happens here. Now, here you've got a force going up of 70. You know what that does? That makes this thing go up. It takes a jump up of 70. That puts you there at 20 kilonewtons. And then there is no change. It just stays at 20. It stays at 20. See, there is no distributed load. This is 0. If there is no distributed load, well, the distributed load is 0. And so that means the slope is 0 of your shear loading diagram. Now, notice the slope here is 0. Hey, we're all done. We're all done. That's it. Well, wasn't that fun? Now let's get the bending moment loading diagram. Well, we've already got 2 points by inspection. I need to know where this is right here. That's an important point because that's where, see, when you write we're going to get the equation of this thing. Let me write the equation of this shear in here. You guys all took math in school, and you're familiar with the y equals mx plus b. They call it the slope-intercept method of drawing a straight line. Slope-intercept, where m is the slope and b is the intercept. Well, see, if you wrote the equation for this shear force, it would be 30. Here's the equation. The shear would be 30 minus, because it's got a negative slope, of 20x. Let's try it out and see if it works. Now, if x is 0, you get 30. Well, that's good. If x is 4, you get 30 minus 80. That makes a minus 50. Yeah, that's good. But see, I wanted to know what this was right here. Well, I don't know where it is, but I know the slope would be 0, or I mean the shear force would be 0. So solve this for me. Say 0 equals 30 minus 20x. And see if you can find out what x is. You know what I think it is? I think it's 1.5, isn't it? You know where this is? This is at 1.5 meters. Okay, and what do we know about it? Well, it's where the shear force is 0. Now we've got another equation. It goes like this. Running out of room here. Here's some room. It goes like this. V equals the slope of the bending moment diagram. Now, if the slope is 0, that means you're at the top of the hill. I don't know if you've ever noticed this, but if you get at the very top of a hill, see, here's a hill. When you're at the very top of a hill, the slope is 0. And see, if the slope is 0, if the shear is 0, look, the shear is 0. If the shear is 0, then the slope is 0. You might try that sometime. Go find a hill and climb up on top of the hill and notice that when you're at the very top, Here, I'll draw a picture of one of us standing there. Look, there we are. We're standing at the top of the hill, and guess what? The slope is 0 there. Interesting. 0 slope at the top of the hill. So it's going to look kind of like that. And we can get the equation. The equation is going to go like this. Now, I had this equation up here a little while ago. I had to erase it. That's one of our 4 equations that I had up there a little while ago. But see, we've got what V is. So here, let's do a little math here now. And we're going to go from 0. This is an important point. It occurs at 1.5 meters. So we're going to go from 0 to 1.5 meters and see what we get. Now I'm going to shut up for a minute, and I want you to find the bending moment. It's a maximum, isn't it? It's a maximum. There's a maximum bending moment in this beam located right in here. That might be the place where it breaks. I'm going to shut up for a minute. I want to see if you can find that maximum bending moment. Here, I'll write it down for you. That's a maximum. Now, it's not the biggest maximum. There's going to be another maximum down here someplace. We'll talk about it in a minute. But it's a local maximum. Okay. Go for it. I'll be quiet. See if you can find what that local maximum is. Well, I wonder if I did that right. Now, when I integrated this, I got 30x minus 10, it'd be 10x squared, wouldn't it? Yeah. Okay, I did it wrong. Let me try again. Okay, now when I did that and I plugged in 0 and 1.5, I got 22.5 kilonewton meters. I'm thinking that this thing peaks out at 22.5 kilonewton meters. Interesting. Well, let's see where it bottoms out. And I think I'm going off the graph here, maybe not. Now to get where it goes off the graph, you just put in different limits. I need some room. Let me put it up here. Well, what I'm after is the bending moment down here when x is equal to 4. There's a little room right here. I'm after the bending moment when x is equal to 4. Well, it's going to be this integral from 0 to 4 of 30 minus 20x dx. See, I'm using this equation right here. And so the bending moment when x is 4 will be 30x minus 10x squared from 0 to 4. We can do that. I'm gonna plug that in now. $30 times 4 minus 10 times 16. I'm getting minus 40 kilonewton meters. This down here, this is a minus 40 kilonewton meters. And then what happens? Well, we're doing great. We could use this equation here. See, the shear is a constant. It's a constant slope of a positive 20. So what this thing does is it comes up here, goes like that. It has a slope of a positive 20. Let's see if it does. Well, it goes from 4 to 6. That's it goes 2 meters. It goes up 40 kilonewton meters. If you divide 40 kilonewton meters by 2 meters, you'll get 20. Okay, now I'm getting mixed up now. You got 40 kilonewton meters, yeah, and the slope is that divided by your 2 meters, so that gives you 20. Yeah, it gives you 20 kilonewtons, so that's what this is. This is 20 kilonewtons. It looks like that. Now here's the important stuff. That local maximum is 22.5. But this is probably the more important one. This is probably where this thing's going to break. It's going to break right here. This thing will fracture. It'll have a problem right there because that's where you have your maximum bending moment. It's also where you have your maximum shear. See it? If there's a problem with this thing, it's going to occur right there. Well, we used the equations, we used inspection, and we used sectioning, but we could check it. This is called checking your work. We could check this and see if we could see if we did it right. Why don't we do that? That'd be fun. We're going to check this and see if we did it right. Okay. Now, if you let's section it someplace. I don't know. How about right here? This would be a good spot. Let's just section it right here. You're supposed to look at a left-hand section. So what do you got? You got 30 going up and 70 going up. That makes 100 going up, 80 going down. So that means you have to have another 20 going down. Well, there it is. There's a 20 kilonewtons going down, which is a positive shear, remember? Right there. Well, that checks. But what about the bending moment? Let's check the bending moment. Okay, well, if you come down here, if you sectioned it, you know what that bending moment is? This is minus 40, this is 0, so that'd be minus 20, wouldn't it? Well, can you see that you got 20 here and 1 meter here? And so you have to have a bending moment here. You've got to have a bending moment of 20 Newton meters. And can you see that it would, well, it's going, okay, now which way is it going? The 20 kilonewton meter bending moment. They say it's going like this, which I think is right, because it would be going this way on the right-hand member, but it would be going clockwise on your left-hand member. But we could write it out. Here, let's write it out. I need some room to write this out. This is called checking your work. It's called checking your work. We are going to look at this left-hand section, and we're going to take the moments about, I don't know, call it section AA. So here we go. Some of the moments about section AA. Left-hand section. Well, you got a minus A. You got a minus 30 kilonewtons times, it'd be 5 meters. See, there's 4 meters plus the 1 meter. Positive 80 kilonewtons times 3 meters. See, there's 2 meters here, and then there's 1 meter there. And then there's a negative 70 kilonewtons times 1 meter. And then you have this bending moment, which is negative because it's clockwise. Negative m equals 0. Now we're going to solve that for m. Plug all that in your calculator and let me see what comes out. Here we go. I'm plugging this in. Minus 150 plus 240 minus 70 equals a minus 20. Now, wait a minute. Yeah, I'm getting the bending moment right here is minus 20 kilonewton meters. Well, look, it's clockwise. It's 20 kilonewton meters, like we said. It's right here. And it's clockwise. Yeah, we just checked our work using method of sections. Any comments or questions on that?
On your shear,
Yeah, go ahead.
on your shear force diagram, does it not go back down to 0?
No, because there's, if you took a section right here, 1/1,000,000th of an inch from the end, you would have a shear force. It's not 0. It's not 0. It doesn't go to 0 there, and it doesn't go to 0 here either. Now, the book, I think, drew a line there. The book is wrong. The book is wrong. But thank you for asking. Now who was that?
Ashley.
Ashley. Thanks for asking, Ashley. No, there's still a shear force in there, and there's still a shear stress all the way up to the end. It doesn't go to zero. No, it doesn't go to zero, but thank you for asking. Anybody else, comment or question? But Ashley, I think somewhere in the book I saw them draw a line going down to zero. Did you see that too someplace? Because I think I saw it, and that's not right. It's just not right. I think maybe what they were doing is, if you wanted to color this, see, I've got a green color here. Yeah, here we go. I'm going to color the shear loading diagram. Yeah, I'm coloring it, making it pretty. There it is. And it goes like this. I think what they did was, when they color it, to make sure they don't go over out of the lines, they'll put a little line there, little green line. There you go. But that little green line doesn't represent a zero shear force. No. It just represents where you want to color it, make it pretty without going outside the lines. Anybody else, comment or question? Okay, well, let's do another one then. That was a lot of fun. This one is 614. It's not a F problem, it's just a problem 614. And we're going to erase all this if that made sense to you. Okay, well, we're going to erase all that. So we do 614. But see, these are important because in a little while we're going to be learning about the flexure formula. Not yet, but I think next time. It turns out when you bend something, then you get normal stress according to an equation that goes like this, which we will talk about soon. It's called the flexure formula. But you've got to have this bending moment. Now, where do you get it? You get it from the bending moment loading diagram. That's where you get it. So we're going to do one. Now, this is 614. Let me find it here. Okay, I found it. All right, we're going to draw this beam. Here we go. And you know the drill. We have to draw the free body diagram. Now this right here is an external couple. It's an external couple. I'll put it in red. And it is 30 kip feet. 30 kip feet. It's an external couple. This is on page 284. Now, how could you apply that? Well, if you had a bolt that was fastened down right here, and you had a wrench, an artist's rendition of a there's this adjustment screw thing there. Pretty pathetic picture of a wrench. But see, if you took this and you swung it this way, like that, you would be applying a twist. You'd be applying a twist clockwise right there. That's what they're doing. They're applying an external couple. And then there's a loading diagram here. And it is 2 kips per foot. They use the symbol W, 2 kips per foot. Two kips per foot loading diagram. This is body A, right? It's a support. It's a bearing, a smooth bearing support at A. And then they've got this 30 kip foot couple there. And they never did label it, but we could call it C maybe. I don't know. Call it C. And then they have B right here. And I'm thinking you're going to have a force going up here and a force going up here. Let's give it names. B would be a nice name for that force. We don't need this pathetic looking wrench there. Now here we're going to have a resultant force. And you know the drill, resultant forces are equal to something. Let's see if anybody listened to me last time, a few minutes ago. Ben Harris, Ben, unmute and say hello, please, Ben Harris.
Hi.
Hey, Ben, how do you find the resultant force of a loading diagram? Do you remember?
So it's going to be your, it's the area of that box.
He's got it. He's got it. It's the area, the resultant of a loading diagram is the area. Ben, good going. So, well, we need to know this distance here. Just a minute. That's 5 feet. There's 5 feet. 5 feet. Ben knows that we're just going to take the area. We're going to take, to get the resultant, we're going to go 5 feet times 2 kips per foot. Remember what a kip is. It's 1,000 pounds. And hey, I can do that. I can do that in my head. I've got 10 kips. That is the resultant. There you go, 10 kips. Ta-da! We now know that we have 10 kips, 10,000 pounds resultant there. But wait a minute. Oh, we don't know A and we don't know B. To find those, we've got to find those. To find those, you have to take moments about a point. Why don't we do moments about A? Moments about A. Okay, well, then we'll have that 10 kips times that distance. That's how you take moments. moments of forces times distance. And that distance is 2.5 feet. Now that's a positive moment. I'm going to ask somebody, how come that's positive? I want to see if they really understand. Samuel, unmute, please, and say hello.
Good morning.
Yeah, good morning, Samuel. Samuel, this is a positive moment. This 10 kips at 2.5 feet. How come it's positive, Samuel?
Because it is
Yeah,
counterclockwise.
he knows. He knows it's counterclockwise. It's going counterclockwise. He knows exactly. Okay. And then there's no moment about A because the force there goes through A. A force that goes through a point does not give you a moment about that point. But this one does. And this is a negative 30 kip feet because it's clockwise. And then you have see, it's negative because it's clockwise. Then you have a positive B times 10 feet. Now, did I get all that right? Stare at that. If I didn't, tell me. And get your calculators and find out what B is for me. Go ahead. And I'll call on somebody here. How about my friend Shane? Shane, unmute, please, and say hello. Earth calling Shane. Earth calling Shane. Come in, Shane. Uh-oh, coffee break. Nicholas, you're not going to let me down. Nicholas, did you solve for B, Nicholas?
I got 0.5 kips.
That's what I got. I got B is 0.5 kilopounds. Let's write it down. 0.5 kips. There we go. Good going, Nicholas. Okay, now we can do sum of the forces and get A. See, the sum of the forces has to be 0 in the y direction. Now we got 10 going down and 0.5 going up. So what does that make A? Nicholas, I'll pick on Nicholas again. What's A got to be, Nicholas?
Sorry, I kind of spaced out there.
Take your time. See, we got 10 going down, 0.5 going up. So what's A got to be?
9.5.
Yeah, good going, 9.5. We got A is 9.5 kips going up. And hey, we're done. We got all the external forces and couples. We're done with that. But we haven't started on our diagrams yet. We had to go through all of that so we could get started on our diagrams. Now I'm going to erase this stuff here. I don't need it anymore. Unless you have a question. Well, nobody said anything, so I'm going to erase this. And now we're going to do our loading diagrams. So we need a shear loading diagram. This will be our shear loading diagram. And then we'll have to have a bending moment loading diagram. Okay, here I'll label this is our X direction, just going to the right. And this is our shear, and this is our bending moment. And remember, we have three ways of doing these diagrams. We have what is known as inspection. Remember that smooth pen right there at B? That can't give you any twist at all. It's kind of like somebody greased the doorknob. So on the bending moment, it's going to be 0. Come on now. Need to get a new pencil, I guess. There, it's going to be 0. I don't see any other obvious things. However, I don't think there's any twist going on at that end. I think that's going to be 0 too. That's my gut feeling on the bending moment. Now, what about the shear? Well, okay. Let's go over here and look at this end. If you took a section, remember there's 3 ways to do this: inspection, sections, and equations. If you took a section real close to the end, I think the shear is going to be 0. If it's close enough to the end. But then what happens? Well, how does the equation go? It goes like, here, let me write it over here. It goes like this. Now the loading diagram's going down, that's negative. So the slope of this is negative. This thing has a negative slope, and it goes and we know that the change in your shear is equal to the integral of your loading diagram. And that's just the area. Well, what's the area? Well, the area is your resultant, which is, we decided was 2, right? So this goes down to -2. Here we go. This is -2 kips. I'll go back over that if anybody needs me to. Just say, Mr. Griffin, go over that, please. Anybody?
Isn't it -10?
I was wrong. I was dead wrong. It's a -10. I was reading the wrong thing. It's the omega is 2, but the resultant is 10 going down. It's a -10. Now, who was that just spoke up?
Ashley.
Ashley got a big fat thank you point there. That's Ashley's. And she helped the class, see, because I put the wrong thing in. Now this is going to take a jump up of 9.5. So it jumps up here 9.5. That puts you at about a half, doesn't it? And I think that half just stays a half. I don't think it changes any. I think it stays a half all the way to here. I think that's it, guys. I think we just did the shear loading diagram, but let's check it. Let's check it and make sure. If you took a section in here, see, the other way of doing this is taking sections. If you took a section in here, you got 10 going down, 9.5 going up. Wouldn't you have to have a half going down? No. You'd have to have a half going up. Well, see, going up on a left-hand member, a shear a shear force going up on a left-hand member is negative, because remember, shear going down on a left-hand member is defined as positive. You would have to have a shear going up of 0.5 to add to the 9.5 to give you the 10 going down. Yeah, we did that right. I think that's it. You can color it in, get yourself a crayon, color it in pretty if you want. But let's do the bending moment. Okay, how do you go about doing that? Well, you could use method of sections, but boy, that would be hard. Let's do the equations. Now you see, we could write the equation for this right here. That's equal to minus 2x, I think. I think that's it. Try it. Plug in an x is 0, and you'll get 0. That worked. Plug in an x of 5, and you get minus 10. That worked. Yeah. There's your equation. Now, if you want the bending moment, the way it goes is like this. The equation there is like that. And see what this is final minus initial. Well, the initial is 0 in this interval right here. So that's just going to equal m. And this here is minus 2x dx, and we're going to go from 0 to whatever x you want. Okay. Well, let's take the integral of that, and I'm getting minus x squared. How about you guys? That's it. And then when you plug in the limits, you get just minus x squared. Okay, well, what does that look like? Well, that looks like a parabola. You guys have all studied parabolas, and you know they kind of come up here, and they peak out, and they go down, da-dun. Yeah. Of course, we don't have anything over here, but this is a parabola. There we go. A little bit sloppy, but oh well. You got the idea. It's a parabola. And if you want to know what this value is right here, well, you can just plug it in. It's minus 25. Can you see that? X is 5. So this is minus 25. Does that show up? Yeah. Minus 25 kip feet. Minus 25 kip feet. Then what? Well, we have an equation that goes like this. V equals the derivative of your bending moment. And this V here is well, it's minus 0.5. Okay, so it's got, I'm going to run out of room here, maybe not. So if this is minus 0.5, that means the slope is minus 0.5. So it's kind of headed downhill here a little bit. Not much, but it's got a downhill slope. There you go. Does that? Yeah, that shows up. Do you understand this is minus 0.5? That's what this is. This is minus 0.5 kips. And so where do you wind up here? Well, we could just get the area of this. How long is that? 10 foot? What's 10 times minus 0.5? That's just minus 5, isn't it? This should be, no, wait a minute, I'm getting mixed up here. If that's, no, I think that's right. I make this minus 30, wouldn't it? minus 30 kip feet to right here. And I think you're, wait a minute, it's got to be 0 here. I screwed up, guys. And I've got 5 minutes to oh, wait a minute, Auga. I forgot all about the 30. I forgot all about the 30. Right here, something happens. We have a external 30 kip foot couple acting that I just sort of forgot about. So what do I do with it? Well, you got minus 25 here. There's a 30 there, but see, that's a negative 30, isn't it? Yeah. It's external. It's an external couple. I think what happens is this thing pops up here to I got about 4 minutes to figure this out, guys, and I'm running out of time, but we're going to make it. Now this is the equation for the bending moment in here. Right? Yeah. And when you take the integral of it, you get minus x squared. What I need is the equation for the bending moment in here. No, that's only good in here. I need it in here. Well, here, let me do it in here. Here we go. Now what that is a shear of minus 0.5 kips. And so when you write your equation for your bending moment, it goes like this. It goes minus 0.5 kips times dx. I'm writing this equation where the v is minus 0.5. Now when you integrate that, what you'll get is you'll get your final bending moment minus your initial, but now the initial is the minus 25, right? So it's a minus 25. You subtract a minus 25 equals, and here we're going from 5 to x, okay? And so what we have is minus 0.5 x, but you have to subtract a minus 0.5 times 5 when you plug in your limits. So what does that give you for your bending moment? Well, that's a plus 25. That makes that a minus 25, and that's, what is that, minus 2.5? What does that make you? Minus 27.5 minus 0.5x. So when x is 10, what do you get here? Minus 32.5. Oh, gee. I've only got a minute or so left. Let me show you what happens. That this is not 32 and a half, it's 27 and a half. This is, the 25 is right. But this goes down to a negative 27 and a half. And then it pops up 30, which gives you 2.5 right here. 2.5. And then the slope continues on downward negative with the same slope that it had before. The slope is negative 0.5. It does not go down to here because it takes a jump of 30 from negative 27 and a half up to 2.5. That's what it looks like, and it goes down to 0. It's sad, but I ran out of time. Hey, these are tricky. These are very tricky. I think we understood everything here, but what's bothering me is this this jump of 30. See, there's a jump from here up to here of 30 kip feet. And why is it a jump? Why is it an increase? Why does the bending moment increase?
Wouldn't it be because those 30 kip foot that you have written there are external and the
Yes.
beam itself has to make an internal positive one?
Yes,
Why?
we're doing internal on this diagram. That's external. Absolutely. Who is that talking?
This is Samuel.
Samuel. Good going, Samuel. Yeah, this is external. And so this is not external. We're doing internal. Yeah, there's a difference, all right. There's definitely a difference. But we're out of time. Hey, do your homework. Now, let me think about this. To be honest with you, I'm a little confused. This is the correct diagram though, because I checked. But we're going to have to say adios for right now. Go work on this. Rome wasn't built in a day. We're going to get it. But I'm going to have to go because I got this other class coming up. Do your homework. We'll see you on Thursday at 9:30. Bye-bye, students.
Bye, Mr. Griffin.
Yeah.
Mm.